Hello everyone. Welcome to the model hosting video in the large-scale machine learning section of ML Expert. This video directly follows the data hosting video, so if you haven't seen that, I strongly recommend it. In the last video, we talked about how we will be using a distributed cache here for our recommendation service. What we didn't do is talk about how we will be hosting our models inside of the recommendation service itself. So generally, let's look at what the service will have to do. First, it will have to fetch the features. This will be oftentimes both the user and the item or product or ad or video features as well. So if we're implementing a video recommendation service, we'll need the features of the user as well as the features of the videos that we want to either rank or recommend. Now, we discussed the fetching of the features in the data hosting video. That's just the very first part though. After that, we need to alter the features in most cases. So after we get the user and the item features, we may have to append one to the other. As well, we'll have to append online features that may not have been able to be stored in HDFS and therefore the distributed cache. So perhaps maybe a feature is whether they're on a desktop or the mobile app. Maybe their particular country is a feature, or the referrer, such as Google or Facebook, is also a feature. After we alter the features, we're going to perform the inference itself. That means sending those features to the model. After the model returns the inference, we need to map that inference to some meaningful result. Let's say the model returns an array of probabilities per item. Well, we actually want to turn that into the recommended item. So generally, all of these things have already been done in the exploration step. When we were training and validating, we had to make sure that all of these things happened correctly such that the model accuracy was valid. Well, in this case, we just have to repeat all of those same things. So we're going to use a tool here to help us ensure that the same things happened in training exploration that happen in production. That tool is called Spark Pipeline. Spark Pipeline is a library provided on top of MLlib, it's sometimes called Spark ML, which allows you to create a DAG or directed acyclic graph of stages required to go from hosted features to usable predictions. So let's go ahead and look at that now. So here we have some familiar code that we've used earlier in the series. We're taking a data frame and we're simply splitting it up into a training data frame and a test data frame. If we look at just the training data frame, we'll see that we have this data frame. Again, this should look very similar. We have the user ID and their interactions with the website, as well as whether or not the particular user's canceled within a week after the last day of the interaction counts. So here what we'll be using is a Spark pipeline. So here from PySpark ML, we'll be taking in the pipeline. And what that means is we will be doing the same things that we did before. So if you recall earlier in the series, we used the vector assembler to create the features column, which encompassed all of the interactions. As well, we're going to use the vector assembler in the same way with the label column. So let's say that these are our hyperparameters that we've tuned with either grid search to take advantage of parallelization or hyperopt if things were very expensive. And now what we can do, since we have our feature assembler, our label assembler, and our model, is equip them as stages in a pipeline. So here, this will be an ordered list, which we will first take our data frame and fit the vector assembler, then fit the label assembler, and then finally fit the model in this pipeline. How we do that is we just call pipeline.fit, given this training data frame that we saw up here. And what that will do is give us a finalized model. Again, there's more to this model than just the logistic regression model itself. It also encompasses these two assemblers, but this allows us to get predictions just in the same way that we would earlier with just a regular logistic regression model. And in addition, we can save this model just like we can any other model, such that we could load this exact pipeline into our production service, such that we're guaranteed that the same exact things will happen in production as in exploration when we created this pipeline in the first place. Again, this is an extremely useful tool when you begin productionizing your models. So we've now covered how we can guarantee that the model that we use in production will be the same exact model that we've used during exploration, And in the previous video, we covered how the data that we used in exploration can be guaranteed to be the same in production because the distributed cache is just bulk downloading all of the data from HDFS every 24 hours. So now what we need to focus on is the quality of service that this recommendation service provides. So with that mainly is latency. Amazon found that an extra 100 milliseconds of latency created a 1% loss in revenue. Google found that an extra zero point 0.5 second load time causes a 20% traffic drop. This equates to billions in revenue. So now that we're getting an ML inference on the critical path of rendering the home page, we're now contributing to those latency increases. So now we have to really concern ourselves with latency. Another problem is that we can't fetch the features from the distributed cache and run the model in parallel. Since the model depends on the features, we have to do these in order. So this time could potentially add up to be quite a bit. So one of the first questions that we can ask when managing the latency is, where do we want to perform our inferences? Do we want to perform them locally in the same exact service that we're serving the traffic as? Or do we want to ship the inference off to a remote inference service? If we were to have the inference actually run on the recommendation service itself, then the latency would be really low. However, it's often the case that your recommendation service is written in a different language than your model inference code. For instance, it could be very likely that you have some maybe Go service or Java service, and the model inference code is in Python. Now, there are some formats that you can save your Python model in, which can be read by many different languages in low latency. So that is something to think about. One of those, PMML, is Predictive Model Markup Language, and that is an option. Something to keep in mind, though, is that when you want to update your model, you will have to deploy to your service. Likewise, if you want to update your service independent of the model, you still have to deploy to the entire service itself. So you get this dependency that you may not want. Another option is to perform a remote inference, so we would have a dedicated inference server, and then all of the recommendation services would call this server. This is great because it's language agnostic. As well, their deployments are no longer tied together. Finally, the inference server could have specialized hardware requirements outside of what your typical web server hardware requirements would be. This configuration could accommodate that. So beyond the local and the remote inferences, we also can look at language optimizations to help manage our latency. So Python is pretty slow. C and C++ is about 10 to 100 times faster, and Java is between 10 and 50 times faster. However, most scientists either don't know or the models they want to implement don't have strong support for Java, C, and C++. So there is a tool out there which is a just-in-time compiler called Numba. Numba compiles the Python code down to machine code, and it can approach latencies comparable to C and Fortran. Now, after we've taken care of the language optimizations, we need to look into which hardware we need. Now, generally, we want a CPU over a GPU in terms of real-time inferences. We mentioned this concept earlier in the series, but the general idea is that the CPU will be faster for these one-off predictions, and GPUs are better for batches. After we've settled on which hardware we want to use, we now need to look at the worst-case scenarios. So we also want low-latency fallbacks and circuit breakers. In this case, if some call from this client to the distributed cache or the client to the inference service takes too long above some threshold, then we should be able to return to the user some low latency recommendation. This could be recommending the most popular products, or it could be something a little bit more personalized. In general, though, it should be pretty fast. Now, as well as just overall latency, if any of these were to go down or there were network issues, we should also have circuit breakers. All this means is that after some number of retries to a down either distributed cache or a downed inference service, the clients should begin automatically falling back to the default experience. Now, this should only happen until these services can come back online. Now, another interesting way that we could perform inferences is by batch inferences. So instead of having an inference server, what we could do is just store all the pre-calculated inferences on the distributed cache itself. So when would this be a good idea? Well, generally, we want minimal or no online features, which we talked about earlier in the video. We also want to make sure that the inference space is small enough. What does that mean? Well, let's say that we have 100 million customers, and we want to recommend 30 titles. So let's say either that's YouTube videos or that's Netflix shows. If we only want to recommend 30 total titles across those 100 million customers, well, if we represent these 30 titles just as an integer, and each integer is assigned a unique title, then we only need to store 100 million of those integers. This would definitely fit in memory and be around 12 gigs. However, let's say that we still had 100 million customers, but now we had 10 million products to recommend in terms of similar products to what a customer has already purchased. Well, that would be about 4 petabytes. We may not be able to efficiently store 4 petabytes of data in our distributed cache. I think that would be pretty difficult. So in that case, the trade-off would be increased latency because we no longer do batch inferences for a decreased cost in storing 4 petabytes of data. Storing the results aside, calculating something like this is definitely not free. In fact, it would be about 1 quadrillion inferences that you'd have to do in 24 hours if you wanted to update your data every 24 hours. And actually, you'd probably have far less time because you would have to transfer 4 petabytes of data in that same 24 hours as well. So this to me seems like not a very good fit for batch inference. This would be better for an online inference like we talked about earlier. Alright, in this video, we talked about how we can preserve the experience that we created in exploration with the experience that we're going to present to users in production. We talked about a tool called Spark Pipeline, which could help us do that. As well, we talked about ways to manage the latency of fetching our features, as well as conducting our model inferences. That wraps up the model hosting video and the large-scale machine learning section of ML Expert. Thanks for joining, and we'll see you next time.